In this lesson, we're going to be looking at how to do transformations of functions, and we're going to learn some really powerful tools that allow us to very quickly graph not just these functions that are being used as examples today, but many different types of functions. You may want to have a graphing calculator handy, and you need to have gone through the lesson on that's called 7 common functions first as well. So if you have a graphing calculator handy, you'll see that for each example, we've got a base function, f at x, and those are the ones that are in the previous lesson. So you should have some familiarity with what those look like and what their table of values looks like. And then you'll see another function that looks like the base function, but has one or more changes to it. So you can, on the graphing calculators, if you use the y equals, you could have the option of y1 equals, and you could put x squared in there, and then y2 equals, and you could put the second function in there, and that way you can see them on a graphing calculator in relation to each other. But always before you actually graph them, do try to make a prediction about what you'll see when you do graph them, okay? So I am going to, in this lesson, tell you the names of the transformations that we're using, and gradually we'll be learning how to, with different functions, look at the function, be able to state what the transformations are, and create what's called a mapping rule, which gives us a fresh table of values to quickly graph the new function. So we're looking, first of all, at vertical translation. So a vertical translation means that the original graph is moving up or down, but its shape is not changing, okay? So our base function is f at x equals x squared, and the table of values for that went from -3 up to +3, and the y values were the squares of those values, so 9, 4, 1, 0, 1, 4, 9. If we sketch that graph quickly, it's remember it's 0, 0, 1, 1, 2, 4, and 3, 9. Oops. And it looks like this. And remember, it's the domain and range. The domain was -infinity to infinity, and the range was y is greater than or equal to 0. Okay, so that's what the original base function looks like. G at x is the same function, but 4 has been added to it. So that gives us a vertical translation. So if we look at that on, let's say, using our graphing calculator, we'll see that it gives us that same shape of graph, but it's been bumped up. And the mapping rule to describe this is all of our xy values. So xy maps onto x and y plus 4. So that means all of the xy values possible for the base function, the x's go to x, so they stay the same, and the y's go to y plus 4, so they all have 4 added to them. So this is called a mapping rule. And the mapping rule helps us create a new table of values because it gives us a formula for what to do for x and y. So our new graph, the x values will stay the same. Oops, yeah, 1, 2, 3. And the y values have 4 added to them. And if I switch colors to sketch that graph, 1, 2, 3, 4. I don't have space on the graph to show the outer points, but you'll get the idea of what's happened with the graph. here. So we still have the same shape, wobbly with my pen today, but it has just been raised up 4, and we call this a vertical translation, and the shortcut is VT, and we say it's 4. And because it's positive 4, that means we've gone up 4 units. So all of the points on the original graph can just be moved up 4 to sketch g at x, our new function. So if we look at example 2, our base function is f at x equals the absolute value of x. So our values there, also remember we went from -3 to +3. And our y values were the absolute values of those. So we had 3, 2, 1, 0, 1, 2, 3. So that gave us that V-shaped graph. And remember, there's a lot more points than the ones on our table of values, but the table of values gives us a really good picture of what that graph is, and we put arrows on the end of it. So that's the base function of f at x equals the absolute value of x. G at x is the absolute value of x minus 2. Notice that we're taking the absolute value of x first and then subtracting 2. That subtracting 2 is not inside the absolute value symbol, which makes a big difference. In this case, we end up with a vertical translation of -2. And if you were to put that into a graphing calculator, you would see that you have the exact same shape as the original graph, but that it's lower, it's 2 units lower. So our mapping rule becomes xy maps onto x and y minus 2. So vertical translations, a number added or subtracted from the original function, only affects the y, and it affects it by adding or subtracting that same number to the y values. So my new table of values, the x's are still going to go from -3 to +3. And my y values are going to be 2 lower. So 1, 0, -1, -2, and then back up. So I'll switch colors again to sketch that one in. And our points are like this. So it's the same, exactly the same shape. It's just been lowered by 2 points. Every point on the original graph is now lower by 2. Okay. As we do more examples and start looking at multiple translations or transformations, and once we learn how they work, this whole tool of being able to state what transformations we see in the equation and being able to write that table of values becomes really valuable. In example 5 here, we're combining 2 transformations, okay? So f at x is the absolute value of x. Remember, -3 to +3. And giving those absolute values just the positive numbers. Then if we look at that subtract 3 at the end, it's after the absolute value is finished. That gives us a vertical translation of -3. So we're sliding down 3. And that +2 inside the absolute value with the x means that we have a horizontal translation of -2. Anything that affects the x is going to be the opposite. So our mapping rule becomes xy maps onto x minus 2, y minus 3. So we can take all of our x values and subtract 2 from them. So we'll start at -5. And for our y values, we'll subtract 3 from each of them. Okay, and so the original one gave us that V that starts right at the origin and is centered, and it's an even function. But once we go through these transformations, at -5, I'm at 0. At -4, I'm down 1. At -3, down 2. At -2, down 3. And then I go back up again. So this is the first example where hopefully you're starting to see the power of being able to recognize transformations and using a mapping rule. Because for the other ones, like the absolute value of x minus 2, it would have been pretty quick to just calculate the new table of values. Whereas this one, because there's, a couple of things happening, calculating a new table of values, especially if we started at -3, we would see just this little notch area of the V, and then we would only see the right side of it. Whereas using the mapping rules, we end up again with a table of values that gives us the central important part of that function, so that we can see where the function is changing direction, so that we can see where the domain and range is going to be for that function. Okay, so once we have 2 or 3 transformations happening at the same time, this becomes a really powerful tool for being able to quickly graph different functions and being able to describe what's happening to them. Okay, we've looked at horizontal and vertical translations, which are like a slide, which don't affect the shape or the orientation of the graph, but they move it either horizontally or vertically, or in the final case, both. In this section, we're going to start looking at reflections, and sometimes they've been called flips. If you did geometry in elementary school, they would have been called flips. So here we're looking at f at x equals x squared. Again, that's our parabola, where we're going from -3 to +3. And then we're putting a negative in front of that. And notice it's not negative x in brackets squared, it's negative x squared. So x is going to be squared first and then made negative. So if you put that in your graphing calculator, you'll see that your first graph will look like this. And that your second graph will look like this, where the vertex or the point in that graph is in the same spot, but the graph has been flipped down. Okay, we call that a vertical reflection. It's a reflection in the x-axis. And so we can call it, the shortcut for it would be just to say it's a reflection and then put a subscript x there. It's a reflection in the x-axis, meaning it's flipped down and the mirror line is the x-axis or something parallel to it. So it's a reflection in the x-axis. The mapping rule, so that we can create the table of values for this, will be xy maps onto x. Our x values stay the same. You can see that horizontally, we're covering the same area, but our y values have all been made negative, their original value. So our x's still go from -3 to +3. And our y values now are -9, -4, -1, 0, and again -1, 4, and 9. Okay, so this is this negative that's before the function gives us a vertical reflection, and it affects the y values. Okay. In this example, notice that the x is made negative and then it's raised to the power of 3. So that negative is inside the function with the x, okay? So our original function went from -3 to +3, and from -27 to +27. What's happening with this one, and you'd have to watch as your calculator is drawing these in order. Your first one, we've seen this one a few times, very steep on the left side and on the right side. If you watch as the second one comes in, what's happening is that it's coming in like this, where it's oops, that one. Let me just grab an eraser here a second. Need to go through these 3 points here, and then over to and so this one has flipped horizontally. So you're going to see fewer of these examples throughout the rest of this course, but it's good to see that we can flip things horizontally as well as vertically. So this would be a reflection in the y-axis. So put a subscript of y there because it's like the y-axis is the mirror of the image there. And to create our mapping rule, we would say that xy maps onto -x and y. So here the x has been changed instead of the y being changed. Okay, so our x's are now at +3, 2, 1, 0, -1, -2, -3. And our y values stayed the same. So at +3, we're at -27. Okay, so our y values stayed the same here. Our x values were the ones that changed. Okay, in this example, we are using f at x equals the square root of x. And we have our original table of values here on the left. And remember, it gives us sort of a one-sided shape, starting at the origin and going up and to the right. Notice here that we have two transformations happening. We have a negative happening outside of the square root, and we have a +3 happening outside of the square root. So since they're not in the square root with x, they're not inside the function, they affect the y value and they are vertical transformations. The negative out front gives us a reflection in the x-axis, meaning it's going to flip down instead of going up as the original function is doing. And the x-axis acts as a mirror, although that will change because of the vertical translation as well. And so that +3 is outside of the absolute value function. So that vertical translation is +3, and our mapping rule becomes xy maps onto x. The x hasn't changed because it's still just x by itself under the square root symbol, but the y becomes -y +3. And I've got the x's in the table of values already. They've stayed the same, and I've added 3. I've made the y values negative first and then added 3. So -0 plus 3, -1 plus 3, -2 plus 3, etc. So when I sketch that, I'm at 0, 3. I'm at over 1 up 2, over 4 up 1, and over 9 at 0. So that gives us a graph like this. Okay, so you can see how it's been flipped, it's been reflected, and it's been shifted up 3. So we've combined those two transformations in one. This will be the last transformation for this lesson, and the others will continue on in the next lesson. This example doesn't do any new transformations, but it combines all 3 of the translations that we've talked about so far, transformations that we've talked about so far. So f at x equals x squared is our base function. So -3 to +3. And 9410149. You'll have those memorized soon if you don't already, because we will be doing these a lot. And then the new function is negative outside of the brackets, and then x plus 3 all squared plus 2. So the negative out front tells us it's a reflection in x. The plus 2 at the end tells us that we have a vertical translation of plus 2, so it's going to shift up 2. And the plus 3 that's in the squared portion with the x, so we've gone from x squared to x plus 3 squared, gives us a horizontal translation. And like those horizontal changes, it's going to be the opposite. So it's a horizontal translation of -3. So it's going to go left 3. Our mapping rule will become x, y, all of the original points, not just these 7 points that we have on our table of values, but all of the points of the function map onto, so they change. So the x is changed by the horizontal translation, so it becomes x minus 3, and the y is changed by the other two, so we've got -y plus 2. So our x's, these are like mini formulas for calculating the new table of values. So all my x's, I have to subtract 3 from them. So x minus 3 means I'm starting at -6. And then -y plus 2 means I'm taking the y values, I'm making them negative because of the reflection, and then I'm adding 2 to them. Okay, so I've got -9 plus 2, which gives me -7. -4 plus 2 is -2. -1 plus 2 is +1. 0 plus 2 is 2. And then it's the same because it's still going to be symmetrical. Okay, so if let me just switch back to black and sketch the original shape quickly here. There's our original quadratic or parabola, if you like. So our new one, we'll sketch these points, -6, -7. -5 at -2. -4 at +1. -3 at +2. And then we go back to 1, -2, and -7. So there are 3 transformations. We still see the central portion of this graph. We see the direction that it's heading in. We see its vertex, which is an important point in any parabola. And we can see the same portion of the parabola as we would have seen in the original graph. That's the power of using mapping rules, because we have already learned the central portion of all these graphs, our base functions and our base table of values that gives us the central portion of the graph. By using a mapping rule, we keep graphing that central portion. If we had started the graph at -3 again, we would only be graphing the right side of this. We would only be graphing this portion of it. So we might not even be sure that we have the vertex or all of what's happening in the graph. So the power of being able to recognize the different transformations to the graph and being able to create a mapping rule for that gives us, again, that important portion of each graph. And that's where we'll end for this lesson.